Hello guys, welcome back to John's Workshop, and this is going to be the first one in a series of workshop tips videos. So we'll probably put one of these out once every 2 months, and I spoke a bit about this in my last video on the welding table, which we're going to be using. As you can see in front of us here, it's multi-purpose, already being used. So these videos are going to be a little bit around really me offloading some of my experience and knowledge that I've been fortunate enough to build up over the years in the sort of work that I've done and the training that I've had, being apprentice trained many years ago, and lots of subsequent jobs, all in engineering ever since, through my whole career. I've been really fortunate that I've had the opportunities to work in some really high-end companies, blue chip companies in aerospace, and also some smaller companies making bits for various different sectors: oil and gas, aerospace, automotive. Been involved in a little bit of fabrication, not a lot, but some knowledge of the sort of trade, if you like, but mainly machining and also the sort of manufacturing engineering side of manufacture of aerospace components. So CNC programming, documentation, quality, all of those different functions in various different businesses. So a wealth of experience, I think, over the years. And one of my roles that I did for 3 or 4 years was working in external supply chain for a large blue chip company, and that got me the opportunity to basically travel the world and get into various different engineering shops doing various different trades, so forging, machining, assembly, those kind of things, and that's been all around the world. So also had some opportunity to see the sort of difference in culture and difference in sort of machining setups around the world in different places. So what I'd really like to do, and it was the original plan of the channel, was to hopefully offload some of that knowledge and experience. So these videos will be all aimed about that. There'll be quite a bit of talking, there'll be a little bit of theory, hopefully not too heavy, and there will be some practical examples as well. So we're going to kick off. The first one, as you can see behind me there on the whiteboard, is going to be all around speeds and feeds, and that's largely, I looked back through some of my videos and looked at what sort of the most questions I've been asked by various people, and there's been quite a few coming in around speeds and feeds. So we're going to major on that to start with. We're going to go through some theory and then look at some practical applications as well. So I'll bring you back in a bit closer at the table, and we'll start this off with some talking around various different things to do with speeds and feeds, and it's going to be largely driven by sort of milling practices, because that's where my sort of background and strength is, if you like. But we will hopefully touch on turning and drilling and other things as well. So in terms of speeds and feeds, there's a wealth of information from a variety of sources that you can go and find, ranging from books, publications, pamphlets, websites, internet searches. There are so many options around finding the right information that you may need. So I've just put a couple on the table that I've got to hand. So Machinery's Handbook has got a section dedicated to speeds and feeds, a whole big section of it. There's probably, I don't know how many pages, but there's a good selection of pages there. I think it's this whole section of the book. There's probably, I don't know, 100 odd pages worth of information there around speeds and feeds. Lots and lots of really detailed information, and lots of write-up, lots of considerations, lots of formulas, that kind of thing. Again, lots and lots of information in there that you can refer to around speeds and feeds. There's something like this, and I've had this since I was an apprentice. This is a Presto book, and it's geared up around Presto tooling, which is high-speed steel predominantly, or high-speed steel cobalt. And again, in there, within that, there is a section all around feed per tooth for end mills, milling practices, recommended speeds and feeds for different materials, that kind of thing. So as I said, lots of reference material, bits around geometry of tools and that kind of thing. So loads of opportunities to get information around speeds and feeds. And I thought it was worth maybe just touching on, just from a milling perspective, some of the differences in tooling available, and we'll probably touch on that later, why it's a consideration with speeds and feeds. So ranging from different materials, so we've got high speed steel cobalt, we've got solid carbide, they're typically the main two, and then you've also got solid carbide and high speed steel with a range of different coatings that are put onto the tool, and all for various different purposes. So when I look at different sort of geometries of tooling, so you've got something like this, which is a ripper end mill, and you can see the sort of serrations in the outside, generally used for removing material fast at deep depths of cut, slow RPM, and just generally hogging material out. We've got solid carbide end mills, and I've picked the biggest ones I've got so that they show up best on the camera. So it is an important point that I'd like to cover, and I often see, the main two tools that you will get are variations on an end mill and variations on a slot drill, and this is a slot drill. So I don't know whether the camera's showing that, but there are two teeth on a slot drill, often incorrectly referred to as a two-flute end mill. It is not a two-flute end mill, it is a slot drill. That is the proper name for this, and if you look at the two teeth, you'll see that one of them is much longer than the other, and it goes past centre, and that's so that you can plunge with this. It's the only tool that you can plunge on a milling machine. You cannot plunge with an end mill, they don't have the right geometry to do that. So the whole idea of a slot drill is you can plunge with it, and you can then slot with it to create slots in components, hence the name slot drill, and that's how it gets its name. And if you think about a drill, typically two flute, that's where slot drill comes from. So that's the proper terminology for one of these tools. So as I said, a range of materials, range of different applications, and also a range of considerations. And if I go back to that same point, so there's a 4-flute end mill. If you look in the very centre of there, you'll see there's a dead spot where there's no cutting edges. If you try to plunge with that, it just will not plunge, and you're liable to break the end mill and cause damage to your component and damage to the machine. So it's important to know those two differences. In terms of geometries, another consideration, so end mills like this is a taper ball nose end mill, so you can see it's got a taper on the outside and it's got a ball on the end. Now you can get taper ball nose and parallel ball nose end mills, but from a speed and feed perspective, very important. So to know where you're actually cutting on this ball, or even on the flank, will change your calculations from a speed and feed perspective, because obviously your radius, your effective radius that you're cutting out away from centre, is going to change and vary. So it's always a bit of a compromise with a tool like this, but it's best to know roughly which part of the ball you're using and base your calculations around that particular cutting point. It's also worth noting that from an end mill perspective, a traditional end mill, and this is a high speed steel end mill, very traditional looking end mill there, 4 flutes. Again, you can see a dead spot in the centre, so this one won't plunge either. But typically an end mill will have 4 flutes, but there are a range of end mills that can go up to 16, 20 flutes that become almost a hybrid at that point between an end mill and a burr, a rotary burr. And typically the more flutes you've got, the lighter the cut you're going to take, because there's space in between for the gash for the flute, and the clearance of the swarf that you cut gets smaller and smaller the more flutes you have around the tool. So these are quite deep, you can see these will take a big deep cut and the material will flow away quite easily. On something that's got many flutes, and I think I've got one I can just pull up. So here's an example. So this is a multi-flute end mill, and you can see that the gully for swarf clearance on this is much less, because there's less space to get a deep gully in. So all considerations around cutting conditions. So what we're going to do now is start talking speeds and feeds and some of the considerations around them. So we'll flip back up to the whiteboard and we'll have a bit of a discussion around speeds and feeds. Right, so I'm going to confuse you all now. So we've done a bit about telling you where you can find reference information from for how fast you should go, what depths of cut, what speeds, what feeds, that kind of thing. And one of the first questions people who sort of novice people or people who are learning ask is, how fast should I run? How fast can I run this cutter? And the answer is, it absolutely depends. And if you look in any book, any web publication, any tool manufacturer's website, they will always give you a range for any given tool, and that is because there are so many variables that come into play. And I've listed, this isn't an exhaustive list, this is just me brainstorming for a couple of minutes. So, and the variables you've got to consider are, what's the material you're cutting, what material type is it, does it work harden, is it soft, is it sticky, all those kind of things. How rigid is your machine? Is it like I've got a home shop machine that's not very rigid at all, or is it a £2 million 5-axis machine tool? And again, I've had experience of both, and that will give you a difference on where you're going to start. What are the machine limitations? So horsepower and also spindle speed. So my machine is limited to 1600 RPM on the milling machine and 2500 on the lathe, so can't go any faster than that regardless. And I've also got some limitations on horsepower on both. They're not big beefy machines that you would find in an industrial environment, so again, need to consider that. How rigid is your component? Is it stuck out the vise a long way? Is it stood off the table a long way? Is it thin sheet, thin plate? Has it, and we'll come on to resonant frequency in a minute, but all of those things are all intertwined with each other. What tool type is it? We've just run through some tool geometries. So is it multi-flute? Is it 4-flute? Is it a slot drill? Is it a taper bore nose? Need to consider that. What material is the tool made of? Is it high-speed steel? Is it cobalt? Is it solid carbide? Is it brazed carbide? A whole list of things there. How far is the tool stood out from the spindle? This is probably one of the most important ones. So is it stood out from your spindle nose by a good long way, or is it really nice and tight up against your spindle? What tool holder type are you using? Is it an ER collet? Is it a hydraulic tool holder with a big beefy back end? Again, lots of variants there. What spindle nose type have you got? So mine's a Morse Taper 4 on the milling machine. You could have a BT40, BT50, big chunky back ends, lots of mass, lots of weight. Again, makes a big difference. Coolant type and application. So are you using coolant or not using any coolant at all? And if you are using coolant, what type is it and how are you applying it? So is it high pressure coolant? Is it low pressure? Is it just a dribble? Are you painting oil on with a paintbrush? Again, all of that will have an effect on your cutting conditions. Harmonics and resonant frequency, that's a big one, and that's linked to all of these other variables. So any one of these other variables will change the harmonics of how you're working, and you'll start to get vibration, chatter, various things like that, and that's one of the biggest things that you'll find in a home shop, at least, that causes problems. We'll probably talk a bit about that. If your tools have got coatings on, what coating is it? What's it designed to do? What's it designed to cut? What's the idea of the coating? What state's your tool in? Is it an old tool that's been used lots of times? Has it got chips and lumps missing out of it? Or is it a brand new one? Is it nice and sharp? And what's your expected life? So you could have if you were on a CNC router, for example, or a CNC machine, and people do have them in the home shops, if you've got a 30-minute cutting cycle that you want to run through and you need your tool to last for that full cycle, you may decide that you want to pull back your speeds and feeds to allow the tool to get through the pit that it needs to get through. What's your depth of cut that you're expecting to take? And again, that could be driven by the geometry of the component or just how fast you want to remove the material. And what's your part geometry like? So again, if you're sort of machining a slot or a pocket, you're going to get swarf building up and things like that, and again, so all have an effect on the ability to cut. So I'm really conscious of the fact now that for new starters that's probably really confusing, and you're thinking, well, all you've done there is confuse me even more than I already was. So what we'll do now is wipe all of that off, and then we'll start to try and put some thought process behind how you can make the best of what you've got. So let's start trying to make some sense of all of those variables. So 3 key questions. Can I run too fast? One answer, yes, absolutely. If you're going too fast, spindle speed wise, you will burn the tool out. Less likely to happen with carbide, especially in a home shop, but absolutely would happen with high speed steel and cobalt incredibly quickly, depending on your material type. So major consideration. Balanced off with that, can I run too slow? Probably not. And this is a myth often that people think you need to be within the range that the book specifies. You don't. The only difference you lose is productivity and speed. So you can run a carbide, I could run a carbide end mill, a 10mm carbide end mill at 300 RPM, and it will be perfectly happy. It will be no detriment to the tool. All it will mean is it will take me 10 times longer to remove the material than I could possibly be going. So it's always best in a home shop to err on the side of caution and try and run at the bottom end of the ranges that you'll get in book speeds to start with. If that's successful, you can then ramp it up until you find the limits of your entire setup. What are the most important things to consider? And there are lots, there are many. There's all that long list of variables we've just been through, and they're all important. But the main 2 are rigidity of your component and machine setup and standout of the tool. So best scenario possible is to have no collet holders in the end of your spindle, to have a collet that fits right up into the spindle and the shortest possible standout of your tool, and to have your component, say on a milling machine, actually bolted to the table without a vise or a rotary table or a chuck or anything like that, straight down to the table, and your head the lowest position down possible. That's your best scenario, and everything that you move away from that, every time you're building an extra interface, if you think of a vise on the table, you've got an interface between the vise and the table, you've got another interface between the jaws and the part, you've then got probably a longer standout of your tool. If you've got it in a collet holder, you've got an interface with your spindle, you've got another interface with the tool in the collet. Every time you build in another interface, you build in inaccuracies and also weaknesses into the system. So always go for the rigidity and standout thing first, and try and get everything as close as possible as you can and as tight as possible as you can to get the best cutting conditions. And the closer to that you can get, the closer to the book speeds you'll be able to run for any given tool. So we'll clear that off, and we'll come back with some maths, some very basic maths now around speeds and feeds. Right guys, I just want to try and demystify some. The minute you start writing things like this on boards, it can put people off, and I really don't want it to. So lots of people will be perfectly comfortable with this. There'll be others that stare at that and just go, that just frightens me, I'm just going to guess. And so I just want to show you how easy it really is. So some standard nomenclature and formula. So these are the formula, very simple formula. And the standard nomenclature, if you look in any book, any supplier's website, that kind of thing, D is always used for cutter diameter, S is always used for surface speed, and that can be in meters a minute if you're metric, or it can be in feet a minute if you're in imperial. N, this can vary, but N is typically used as your spindle speed, and that's always measured in revs a minute. Well, yeah, for most applications it's in revs a minute. It can vary depending if you're into really deep stuff, but for everything machining it'll be in RPM. And pi is a constant. Hopefully everybody's familiar with that from school. If you can't remember it, if you don't have a calculator that's got a pi button on it, don't worry about it. I mean, most mobile phones these days have got them on anyway, but 3.142 is a rounded up number, or if you want it a little bit more accurate, 22 divided by 7 will give you a more accurate number of pi, or you can use a pi button on a calculator. two formulas. So this is for calculating, so you've taken your book speed for a given material and you want to know what your RPM is, so N being your spindle speed. So for the metric people it's 1,000 times whatever the S value is out of the book divided by pi times the diameter of your cutter. For the imperial guys, same thing, it's 12 times whatever the surface speed is out of the book and divided by pi times diameter. So for both cases the bottom side of the equation is the same. For the top side, that's your difference between imperial and metric. So I've done a worked example just to show this really is easy. So this is for cutting steel and it's for using a high-speed steel type cutter, the sort of values. So taken a book number, and I've taken that straight out of the Presto book that I showed you earlier. So 24 meters a minute surface speed for S for metric, or 80 feet a minute for our imperial friends. And I've taken a cutter diameter of 12.7, which is unlikely that you would buy a 12.7mm cutter, but I've done that so I can show the difference with a half-inch diameter cutter. The maths is largely the same. So dead easy, plug the numbers of S and D into this. You know, they're the only two numbers you need. 1,000 is a constant, pi is a constant, so the only numbers you need are the S number and the D number. 1,000 times 24 divided by pi times 12.7 for the 12.7 cutter gives me a spindle speed of 601 revs a minute. And if I do it through the imperial one, 12 times 80, so again 12 times S, which is the 80 feet a minute, divided by pi times a half, because it's a half-inch cutter, so 0.5, and you can see there that's come out with 611. So there is a difference between the two, and that's just lost in the rounding between 12.7 and half-inch. That's what's driving the difference there, but largely the same number. So dead easy, dead straightforward, nothing to be frightened of if you've not done this sort of thing before. There'll be lots of guys that are watching this and just going, yeah, get on with the next bit, I know this stuff. So we'll wipe that now and we'll come back with the next piece of the jigsaw puzzle.